Welcome back, folks. We're going to start something a little different today. We're going to talk about what happens when voltage and currents are changing in a circuit. I've mentioned a few times how the first part of this class is really similar to studying statics in mechanical engineering, since I have a lot of you in mechanical engineering. And the second part is really dynamics. Things start to move, and that's what we're going to start looking at today. Rather than throwing you into the deep end and saying anything can move any way at once, we're going to limit ourselves to one case. And for this class, we're only going to start off with this one case. And that's something that is frequently called AC circuit analysis, AC standing for alternating current. All right. The reason we limit ourselves to that case is really twofold. The first is if you're watching this on something plugged into a wall right now, or even if you charged your battery earlier today, the voltage across the prongs of the plug that you plugged into the wall was a sinusoid. Okay, it looked sinusoidal. It was either, we could represent it either as a cosine or a sine function that you learned in your pre-calc classes. So that alone, power distribution, is a huge reason why studying this type of analysis is important. But there's a much larger one in that there was another old dead guy, French guy, Fourier, mathematician, figured out that we could take any periodic signal, so that's a signal that repeats, and we could break it into a bunch of sines and cosines at different frequencies. So now if you can do analysis on an individual sine or cosine, and how that affects the circuit, then you can do that on all of the individual sines and cosines and then put them back together using superposition. That's why we studied superposition. For this class, we're only going to look at signals signals at a single frequency. Okay, so but that's the stepping stone. That's how we build up to the next class that I teach, where I think most of you don't take it with me, but those of you who do, and those of you who want to, I'd love to have you. We're not just looking at analyzing any circuit, but we want to be able to analyze any circuit responding to any signal. All right, so this is how we build up to that. We have to be able to analyze a circuit responding to a sinusoidal voltage supply or current supply. All right, the way we do this, since we want to avoid differential equations as much as we can for this class, is we represent our sines and our cosines, that are our voltages and currents, we represent them as something called a phasor. And the phasor, let's look at the definition. Here we go. Ready? Okay, so the phasor is just a way that we can represent that sinusoidal function as a complex number. So all of the stuff we've done up to this point in the semester, really what we're doing is redoing it, but we're redoing it with complex numbers. So if we can get comfortable with complex numbers, then we can avoid differential equations. So it's kind of a pick your poison thing. Complex numbers, I know some of you are already going, I don't like complex numbers. I'm going to try to give you a good review on them, so that you can do what you need to do for circuit analysis. I'm not going to make you an expert, but I'll give you the knowledge you need to use them in performing circuit analysis. That's the goal here. Okay, so that's a more formal definition of phasor. The definition that I prefer is a vector that spins. So we're going to represent these complex numbers as vectors, and I'm going to draw some pictures in a moment here. And we're going to think of that vector as spinning. And if we spin it around, then we can recover the sine or cosine that the complex number represents. So it's pretty neat stuff. I enjoy this. I don't know if I can make you love it the same way I do, but the deeper you get into it, it's really kind of a beautiful little part of circuit analysis. Okay, so let's talk about how we represent complex numbers, just so that we're all on the same page there. Then I'm going to give you kind of a choose your own adventure assignment. If you feel like you're good with complex numbers, I'm going to let you skip the next chunk of videos, and hopefully you can survive. If you find that, or if you think that you need a good review, by all means, go watch them right now. if you think that you're good and you skip them, and then you get deeper into the material and you think, maybe I should have watched those, go back and watch them. Okay, so it's not necessary. Some of you are going to be all set with complex numbers, know how to manipulate them in your calculator, you'll be good to go. Some of you are not, and that's okay too. So there's a bit of a detour if you want to take it in the videos. You'll see that in the web work. Okay, so a vector that spins. So we've got to represent numbers, and I want you to think about how you represent numbers. And really, since your first days learning how to count, and I've been doing this more recently with my kids because they're about that age, you learn how to count. You go 1, 2, 3, 4, 5, 6, 7. You know, like you count your fingers or whatnot. And you know, at some point you learn that there's this number 0 that means nothing. That's kind of fun to do. And then at some point later in your education, you might learn that there's negative numbers. So we go the other direction as well. And that's kind of the point, is that a number has two pieces of information that it can provide to you. So a number, let's do this. Let's use the symbol. A number tells us two things. Distance from the origin, and direction from the origin. Okay, so when you were learning how to count 0, 1, 2, 3, 4, 5, 6, you were really just going in one direction. Then when you learn negative numbers, you learned how to go the other direction. So if we had, let's start out with the number positive 2, okay, and let's put it on a number line, because really what I'm going to do for you over the course of these next videos, and this video and all of the review videos, is try to show you that with complex numbers, the most important thing is everything we did in one dimension extends to 2 dimensions. And that's really what makes complex numbers special. I usually ask the class, what's a complex number? Somebody eventually gets to the letter I, although electrical engineers use the letter J because I is current for us. And I say, okay, great, why is that special? And they go, well, it's the square root of -1. And I go, yeah, but is that what makes it special? Turns out that that's not the most important thing about complex numbers. Complex numbers are the extension of one-dimensional numbers into 2 dimensions. So if I take +2 and I put it on a one-dimensional number line, I get the distance from the origin and I get direction, right? Because if I said -2, let's do that, and well, maybe not in orange. I want it to contrast a little more. If I say -2, I'm going to get the same distance from the origin, but I'm going to get the different direction. So with these numbers, which we would call scalars, we have the magnitude and we have the sign. So we get the distance and we get the direction. Okay, and it's as simple as that. That's what's in a number. We can say, let's see, we can say, what's the number -3 on a number line? I'm trying to make the colors match here. All right, and I could drop down -3 on a number line. All right, so now we take 1, 2, 3 steps, and the negative tells me that we're moving to the left on this particular number line. Okay, so we get distance and we get direction. That's what we start with. Now, let me pull up the next set of images here. I got a whole stack of them over here for you, but they're not exactly in order. Hold on. Okay, we got something new over here, huh? So we're going to extend this to a 2-dimensional plane, and we can still locate these numbers, right? We can say +2 is along here, and we call that the real axis. Okay, and let's see. So this is still +2, and we also have -3 here. Okay, but with the two-dimensional axis, now we can represent numbers that are not on that real axis, on that single dimension. We can move off that. I think that the name imaginary numbers, I think that the name complex numbers are horrible. I've heard the name lateral numbers thrown around. I kind of think that's better. It's not just how do I move along this number line, but how do I move sideways, up and down in this case. Lateral numbers. When I talk to my kids about it, I talk about them as sideways numbers. How do we move sideways? So if I want to locate this point, I can't do that with just a scalar value and a sign. I need some more information, but it's still a number, and it still has two pieces of information. It has the direction, and it has the distance from the magnitude. So by convention, we start with 0 degrees along the real axis. Okay, so this is 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Although, let me scroll up a skosh here. We can also talk about this as negative 90 degrees, negative 180 degrees, negative 270 degrees, and this one over here is also 360 degrees. It starts to wrap around. So if I want to represent that point on a complex plane, I can measure this angle, and I promise you that it's 125 degrees. And I can measure the distance from the origin, and that's 4. Okay, so I can call this number, I can write it as 4 at an angle of 125 degrees. And that's just one way I can locate that point. There's two other ways I can do it. And we're going to dig into that a little bit more in this video. Okay, so the 2, we can really think of the 2 as 2 at an angle of 0 degrees. Okay, because that's along the 0 degree line, and it's a distance of 2. So again, I get distance and I get direction. Negative 3, I can think of as 3 at an angle of 180 degrees. Okay, we get distance and we get direction. Everything we do in 1 dimensions extends to 2 dimensions. Okay, so I want to talk briefly about how we represent complex numbers in 3 forms. And I just gave you one of them. I gave you what's called polar form. Okay, so let me scroll down here, get a little more room, and cue up the next picture. Okay, so here's a point on a plane, and all we have to do is figure out how to describe where that point is in relation to the origin. So I think of this as a vector. It's going to point from the origin to that point, just like that. And the first form that we're going to use, and this is one that we're going to use not exclusively, but we're going to use polar form a lot. And I find that it's, at least when I was learning complex numbers, it was kind of an afterthought. We learned one of the other forms, the next one, rectangular, and we did a lot of work with rectangular forms, and then polar was like, oh, you can also do it this way. And I find that students tell me that that was the case for them as well. And when it gets to sinusoidal representations of voltages and currents, it turns out that polar is a lot more effective in terms of doing this mathematics. Okay, so this is polar form, and we're going to get our direction is going to be from a is going to be an angle measured from the real axis Okay, so the real axis is 0, and just by convention we think of the counterclockwise direction as being positive. Positive in the counterclockwise. Everybody good with that? Direction. Okay, that's kind of by convention. So we're going to measure our angle here. Okay, and that'll give us our first bit of information. And then our distance is the magnitude of the vector. So magnitude, think of magnitude as length in this case of the vector. Okay, but remember, it's going to spin. I promise you it's going to spin. But we got to do this first. Okay, and in this case, that magnitude, let's see. I knew the number a second ago. Let me go get it. It's not that one. Were you hoping for a good polished lecture? Because I'm used to doing this live, and I'm trying to do all the pictures and animations that I'm going to bring you. I'm trying to do it here, but I feel a bit like the Wizard of Oz with lots of levers and things that I need to pull. Okay, so we measure the distance to that vector counterclockwise from the real axis, and this one is 36.86 degrees. And then we measure the length along this orange vector here, and we find that the distance is 5. Okay, so I can take that point and I can represent it as 5 at an angle of 36.86 degrees. Okay, maybe it's a voltage, so we could throw a unit on there. It's volts. If it was a current, it could be amps, whatever you need it to be. But that's what we're after. So we can uniquely identify a point in space using the distance from the origin and the angle. That's polar representation. That's the first one. Okay. The second one that I want to play with, let me go get do I still have it on my clipboard? I do. Look at me. Same point in space. Identical point in space. But we can represent it a different way. We can represent it using what's called rectangular form. And this is the one that was a little more abused in your high school classes, your pre-cal classes, wherever you ended up taking your math. So rectangular locates the same point in space. And as long as it locates the same point in space, we can say that it's an equivalent number, even if it's in a different form. The way rectangular form locates that point in space is by measuring the distance along the real axis. Okay, so we're going to come right out to here, and we're going to measure that distance. And that looks like it's 4 units away. So let's mark that and say that length is 4. Okay, then it measures the distance parallel to the imaginary axis, the vertical axis. Okay, what's that distance? That distance is 3, but since it's along the imaginary axis, we give it a basis vector. And like I said, electrical engineers use J. J equals I equals the square root of -1. We still don't know why that's interesting. Look at the review videos if you want to dig into that. Okay, it's not that interesting if you ask me. Turns out not many people ask me. Okay, and then there's our vector along there. So we can, I didn't finish this off. This is J3, right? Because it's 3 units up along the imaginary axis. So then we can put those together, and rectangular form is going to look more like this when we put it together. That point in space is 4, we call that the real part, plus J3, we call that the imaginary part. And that representation is equivalent to this one that we see up here in polar, because it gets us to the same place. Okay, so we could rightly grab this one. Okay, bring it down here, and we can say that that is equal to 4 plus J3. They're equivalent, same point in space. I did a little bit of rounding on that angle. I apologize. Okay, so from this we get direction. We get the, where do we get direction from? We get the combination of real and imaginary parts. It's a little bit like finding a grid location on a map. You get, you know, the distance along here, you get the distance along there, and then you figure out where it is. So we get the direction that way, and we get the distance. Okay, along each axis. It's broken up into two parts a little more explicitly. Okay, so that's another way that we can represent it. The third way that we can represent this number is, oh, I lost my picture now that I cut and pasted something, is related to polar form, but your calculator uses it. Well, some of your calculators use it. You TI-84 folks, you're in for a world of hurt. This form is called exponential form. So we're still trying to find that one point here on this two-dimensional plane, exponential form. And it's going to be this vector that we're trying to represent. And we're going to do something similar to polar, but it's going to look at it a little different. And it's thanks to a guy named Euler, a Swiss guy named Euler. And he said we can take the, what order was I doing this in? Direction and then distance. Direction and distance, you know what? I'm just going to cut and paste it. Let's do it, right? Because it's essentially the same from up here. It's the same information as polar. Look how easy that was. I can make my notes quick. Okay, but he chose for some very good reasons mathematically to say, hey, I'm going to measure that there, and then I'm going to measure this. So this is 36.86. Was I right about that? 36.86 degrees. As I scroll around, 36.86 degrees. Okay. And he chose to measure his angle in radians. Okay. So instead of 36.86 degrees, let's figure out what that is in radians. And I have that in my notes somewhere. Same angle, but it's 0.643 radians. Okay, and the distance here is still 5. So the form that he put this in, with good reason, was to say that number is 5 times the natural constant e raised to the j, so we have an imaginary exponent, 0.643. And that's another way we can locate that. The TI-83s and 4s like that format. They don't do polar form, they'll use exponential form. The same information's there. The angle from the real axis and the distance from the origin. So the same information's there. Sometimes you'll find books get sloppy and do something that's mathematically not correct, but still gets the point across, and you might see something like this, okay, where you have that in degrees up there. But if it's going to be mathematically correct, and your calculator's going to want that, if it's an 83 or an 84, then this should be in radians, okay? And that's equal to 5 at an angle of 36.86 degrees. It should be written as 5 e to the j 0.643. Okay, and then we have 4 plus j3. They all locate the same point on a two-dimensional plane. So they're all different ways of writing numbers. Don't you miss when it was just like plus and minus, and those were our two options? Now we have all sorts of other ways we can locate a number on a two-dimensional plane. Okay, next video is going to take these representations. It's actually going to take this one right here. We're going to take that representation, and I'm going to try to make a graphical argument using some animations in order to convince you that we can represent a sine wave or a cosine wave using this complex number. We're going to make it spin. Okay? That was long. I hope it was useful. Stay tuned and good luck.